You asked for it, and now it's here. Hey guys, and welcome back to everydAI. Today is the first episode of the AI 101 series, which you guys asked for after my How Does AI Work video. So the goal of the series is to provide a more technical explanation of a lot of the different factors that go into developing and using artificial intelligence. These will not be every week, so right now I'm thinking that they're going to be every other to every 3 weeks so that I still have the normal content about how you interact with artificial intelligence in your everyday lives, interspersed in the middle, but it will be a recurring series. Also, before we get started, I wanted to let you guys know that as of this morning, my Patreon has officially launched. You can go to patreon.com/everydAI if you'd like to support me as I try to expand the types of content and the quality of content that this channel provides. And while I'm not yet eligible for monetization on this channel, the goal would be that by the time I am, I would be able to keep the channel ad-free through funding from Patreon. So I know if you don't have money to spare, then definitely don't feel the need to become a patron. I totally know the feeling. But if you do have a couple dollars to spare, then definitely check it out. Okay, let's get started. So if you haven't seen the conceptual video, I'll link it somewhere around here because we're going to be referencing some of the stuff that I talked about in that video. As a quick summary, we talked about how AI, specifically deep learning, uses thousands of computational neurons to develop a nonlinear formula that relates input variables to output variables. In that particular example, we were discussing a subfield of AI and machine learning, which is called supervised learning, and that's going to be the focus of today's video. To define it simply, supervised learning is the task of relating a set of input variables to a set of output variables. It requires us to use data that's been labeled with a specific class or set of classes, so maybe a movie genre or a type of food, so that we can then figure out what attributes in that data relate it to that class. And ideally, the resultant formula will be an accurate way of predicting what class an item or data or object or whatever belongs in based on the attributes it has. Okay, that last part had a lot of details built into it, so let's break it down into 4 steps. First, you need to get data. Second, you need to label your data. Third, you need to develop your formula. And fourth, you need to use your formula on new data. Supervised learning starts with figuring out what kind of data you want to look at. So that might be pictures, it might be a 3D image, it might be one-dimensional data, so a set of variables or information that you have about a certain thing. But you need to know what kind of data set you're going to use before you can label it. Our next step is labeling the data. So depending on what you want from your model, you may choose to give your data one label or you may choose to give it several. If you're using niche data, you might need an expert to analyze it. So things like medical data where you're looking at radiation images of tumor progression, or if you're looking at vital signs and trying to figure out if someone has diabetes, that's not really something that the average person is going to know how to label. But a general practitioner or radiologist definitely would. Once the data is labeled, we need to develop a formula that relates the data to those labels. And so this is called model selection. There are a lot of options for doing this, ranging from simple to pretty complex. On the simpler side are linear and logistic regression, which map either a straight line formula or an exponential formula to your dataset. On the more complicated side are neural networks, which use those computational neurons that we talked about in the How Does AI Work video to derive a nonlinear formula that fits your data. To delve into neural networks a little bit more, these computational neurons are called perceptrons, and they are essentially mini linear regressions. They take in data or information either from the original data source that you put into the model or from another perceptron that was in an earlier layer, and they compute some output, usually based on a weighting factor and a bias factor. The nonlinearity is then introduced through something called activations, which are essentially nonlinear formulas that are applied to the output of a perceptron. One of the most common ones is the sigmoid function, which takes the full range of outputs for your data and maps it to a number between 0 and 1 on this kind of curvy graph. Now that we have a model, we need to train it. In most cases, training a model involves making an initial guess at the formula that relates our variables to our labels, trying it, and then seeing how right or wrong we were on any particular set of data. From there, we adjust the formula that we originally came up with until we get to the right answer, or as close to the right answer as we're going to get. Many models do this through something called a cost function, which is essentially a way of quantifying how right you were on any given try. For every right answer you get, you don't add anything to the cost function in most cases, and for every wrong answer you get, you do add something to the cost function. So the more you're wrong, the bigger your cost function is going to end up being. Now, there are ways to tweak your cost function if you're interested in penalizing your model for being wrong on certain types of data. This is pretty common if you have a data set where you have a lot of samples of one type and not a lot of samples of another type. A great example of this is something like epilepsy. When we use machine learning for epilepsy, most of our data isn't from active seizures, it's from just normal brain signals. However, if you're wrong on the actual seizure data, that could cost someone their life. So you want to penalize the model for being wrong on the seizure data more than you want to penalize it for being wrong on the non-seizure data. On the other hand, simpler models like linear and logistic regression might use something like an R-squared, which represents how well the model captures the relationships between the two variables. Once our cost function is low or our accuracy is high, it's time to test it out on new data. Usually, when we originally collect that data set that we got in the first step, we actually remove about 20% of that data so that we can use it for testing. This is because while a high accuracy on your training data might be a good sign, it could also mean that the formula that you've developed is too specific to the training data. That is, it has overfit to exactly match the relationship between the input variables and the output variables. In those cases, these models don't often perform well on data that's never seen before because that data doesn't fit into the exact details of the training data that you gave it. So if you get a high accuracy on your test data, then you probably have a solid formula. It's pretty common for the accuracy on your test data to be a little bit less than the accuracy on your training data, but if it's significantly different, then that probably means that you need to go back and reconfigure your model or your data. There's a lot of ways to troubleshoot when your accuracy on your test data or your training data isn't very good, but I could make a whole other video about that, and that will be another video in this series. So to wrap it up here, thanks for watching the first episode of AI 101. If you like this more technical take on my How Does AI Work video, you can let me know by smashing that like button and subscribing to my channel. This series is one of the things that I'm really hoping to expand via my Patreon, so if you're interested in getting a sneak peek into the topics that I plan to cover in the series for any given month, you can go to my Patreon and become a patron because that's actually one of my Patreon perks. Otherwise, you can find me on the Twitter, and I'll see you guys in the next one. Bye.